Although viruses such as COVID may seem random, many factors impact the overall growth of a virus, as this can be predictable. We can model this using a computer program. The factors are the population of the city, the amount of time one meets with another every day, the probability of infecting someone every time you meet, and the time it takes for a patient to recover. From the test, we can get these results: the amount of people infected, the time it takes for a virus to wear off, and a unit of measurement called R0. R0 is a way to measure the infection rate of a virus. It is the average amount of people a single infected person will infect before recovering themselves. And now let's move on to the coding. I finished the first section of coding. This works by using a random chance for someone who comes in contact with the infected person to become infected. Of course, these values can all be modified manually. If we plot the first 8 days on a line graph, this creates the exponential growth we expect. Great, my code is working. Although, this isn't how the real world works because of immunity and other factors. In my next version, I added consideration to immunity and many other factors. If you plot these points, the simulations now look like this. In this graph, blue represents people infected and red represents immune people. Take a minute and you'll notice something strange going on. So why does the amount of people who are infected go down after a while? And how does the results jump down from 135 million down to 0 people who are infected? No one ever received any vaccines in this model. This phenomenon is described as herd immunity. When enough people are immune to the virus, the amount of people that an affected person infects before recovering is less than 1 on average. Now, even though people are still getting affected, there is a faster rate of people becoming immune than people getting affected, meaning that the virus will die off on its own. This could also be stated by saying that when R0 is less than 1, the virus will once again die off on its own. This model is currently using the race-drill technique opposed to delaying and vaccinating, where there are minimal regulations in place but no vaccine is being developed. This allows us to see the movement of the infection without the complexity of vaccines. In COVID, there's regulations set in place to prevent us from meeting each other. So, why is this so important? To answer this, we can run 4 separate tests, each having a population of 10,000, each starting with 10 affected people, each having a 10-day recovery period, a infection probability of 0.1, but these tests will all have varying contexts: 1 person, 3 people, 5 people, and 10. When plotting these points, we get these 4 graphs. We see that the sets of curves are similar, but once you add in the total amount of people infected, there's some change. Now you see, by just meeting 2 other people a day, it can have huge effects on the virus. I noticed that there's a linear growth with the infected population to the amount of people one meets every day. With a bit of math and a virus with a 10% infection chance, there is around a 1.2k growth of infected people every one more person one meets every day. Now I've added in people dying in new bursts. If we run simulation now, we see spikes in the virus. We see that the first 3 spikes are quite large, then the virus dies off into small spikes, eventually having its final spike and disappearing. The spikes are caused because when R0 goes below 1, the virus is dying off on its own, but when new children enter the simulation, they push R0 back above 1. This is what creates spikes in viruses.